All right, you're up and running. I hope you guys are doing okay today. We are in class number 21. We are going to be talking about how do processes that are currently executing on a computer system talk to each other. So we are going to be focusing on communication between processes uh, as part of our one of the components that is under the management of an operating system. So let's take a look at a lot of different ways in which we can classify this particular communication, right? So first of all, let's talk about why do we need communication in the first place? Well, there could be several advantages because of two or more processes that are currently executing to communicate with each other, right? So you can make each process a particular module or a subtask, and then you can pass information from one process to the other. So for example, if you have think about like a data acquisition system, right? So if a data acquisition system is acquiring all this data and then it is giving or passing some information to a subsequent module, which is say a control system, which is maybe actuating a motor, right? So there are three different modules. In which case, you may be interested in passing messages from the data acquisition system to the control system to the actuating of the motors. And if they are all running at the same time, there should be a way for communication to go from one process to the other. Now, if we go back and think about why we can't do this without a particular mechanism, right? There has to be some communication mechanism in place. The reason why we cannot do it without such mechanism is because every process will generate some virtual address, right? So virtual address to talk to the memory, either to read a read from the memory or to write from to the memory. It'll generate a virtual address. That virtual address will be mapped to a physical address by a page table or a TLB. We looked at all those issues. But the thing to note there is the memory space, the physical memory space of each process is unique, right? So there's no way for a process to overlap with another process in terms of their shared memory. And because of that, they would need there is a need for another explicit sort of mechanism for processes to communicate with each other. So let's start talking about different ways we can classify such communication, and then we'll take a look at how can we use pipes to pass messages from one process to the other. So that's the goal, right? So what is a cooperating process? Well, what is the opposite of cooperating? Well, the opposite or the counterpart of a cooperating process is an independent process. An independent process is one which cannot affect or be affected by the execution of another process. So suppose you have process 1 and process 2. If each of those processes cannot affect change in the other, or they cannot be affected by the other, then those are going to be classified as independent processes. And in this case, communication is not necessary because they are not affecting any change in the other process. But the other side of the coin, other type of process is called the cooperating process, in which case you need inter-process communication, some mechanism that can be used to share information. What is a cooperating process? Well, this can affect or be affected by the execution of another process. So this could be a parent-child relationship, or these could be two processes that are that do not have a parent-child relationship, but they are cooperating, which means that they can affect change between each other. So that's what we are talking about. All the processes and the classification we will look at today is going to fall under the category of processes that are cooperating. What are the advantages of process cooperation? Well, we can share information. For example, we can access a shared file. We can increase computation speed up. How is that possible? Well, if you have multiple processors that are available that can concurrently work on subtasks within a process, then because now you have a mechanism to communicate between one process and the other, essentially that subtasks, then you can effectively use the multiple processors that are available. So that allows the user to get computation speed up. Next, modularity and reuse. This is another advantage of process cooperation. What are we talking about over here? Well, I can take a process and I can break it down into meaningful modules, just as I talked about in the previous example. Data acquisition system, control system, then a output, say, activating some motors. So these are meaningful modules, and I can have each of these modules as a process, as a cooperating process that is concurrently getting executed. So I've made things modular. I can reuse these modules. Not only that, but if there is any sort of error or troubleshooting required, because it is modular, I know where the problem could lie, and that could lead to easy troubleshoot. And it also increases the convenience for the user, because now they have the user can have multiple processes, each of them being a simpler and a meaningful task, allowing the user to get high degree of multitasking. So multiple processes that are working together, it's like process 1 is working, process 2 is working, process 3 is working, all of them are working for to maybe solve a bigger problem, right? They are modules, they are small processes that are concurrently working, and if they have to solve a bigger problem, then they need to communicate between each other to pass information, to maybe access a shared file and so on. For that to happen, we need inter-process communication, or IPC. If we did not have IPC, the way we have structured our computer system is that CPU, virtual address, physical address, memory, and no process can sort of take charge of the allocated space for the other process, right? Because we said some users might be good, some users might have bad intentions, so we need protection, right? So we need privileges. In a kernel mode, in a privileged mode, sure, you can do that, but we are talking about user processes right now. So for all this information sharing to occur, we need a communication mechanism, which is what we are talking about in inter-process communication. So we'll take a look at many different ways this inter-process communication, or IPC, can happen. But before we do that, what is IPC? Well, it is just establishing a link between communicating or cooperating processes. So if you have two processes, for example, process P and process C, this could be parent and child, or it could be process 1 and process 2, or it could be producer and consumer. We are going to use it in different contexts as we go through this lecture. So you're taking two processes and you're saying that process P should be able to write to process C, or process C should be able to effect change in process P, right? So we are talking about passing messages, information from one process to the other. Now, the link that gets established between these processes could be unidirectional, or it could be bidirectional. Generally, you would want a link to be bidirectional, but sometimes using buffers, you are limited to unidirectional capability. Unidirectional essentially means that one process can only affect change in the other, but it cannot happen the other way, right? So P to C or C to P, both cannot be happening at the same time. Bidirectional essentially means it's a two-way communication. So P can pass a message to C, or C can pass a message to P, right? And we are going to be relying on send or receive system calls or primitives to exchange data. And these system calls appear in different variations. These are OS specific variations could exist, but in general, you can express them as send and receive. Those are the system calls, and you pass information to that system call in the form of process ID and a message identifier. So if I can quickly say, this is a message identifier. So it's not the actual message, but it is an identifier that points to a message, right? So if you say you want to send a message to process P, then you say send from the originating process, you say send to process P, their process ID over here, and a particular message identifier goes over here, which points to the message that you want to send to that process. And suppose you wanted to receive message from a particular process, then you say receive process ID of the process that you want to get the message from, and another message identifier where you want that message to actually get written to. You point it to a message identifier. So send and receive primitives can be used to exchange data. And we'll see some examples of this. And as I said, many OS specific variations exist for these system calls. Now, we are talking about two processes here, but you can extend this conversation to multiple processes. But the way we are going to classify inter-process communication, sometimes you're talking about only one pair of processes, and in some other case, you may be talking about several pairs of processes, several links in parallel. All right. Now, in general, there are two approaches to inter-process communication. The one that is showed on the left, that is shown on the left, there is a process A, there is a process B, and as you can see, these arrows are also in relation with the kernel. So that is a message passing approach. A message passing approach in which there are mailboxes, right? These are mailboxes. So each of these process A, suppose process A wants to pass a message to process B. How does that happen? In message passing approach. Well, process A will use a mailbox or a port, right? So these are also called ports or ports. They are going to use this mailbox to send a message not directly to process B, but they actually send it to the kernel using that same send and receive system call primitives. And then the kernel is the intermediary over here that will relay that information to process B. So message passing tends to be slower because the kernel is involved, and it is usually a good thing for small amounts of data or messages. So a kernel is involved over here. Now in the on the diagram on the right, that is called shared memory approach. In shared memory approach, suppose process A wants to send information to process B, and the process that is initiating this communication is process A. If that is the case, the first thing that process A should do is allocate some memory space called shared over here in its own allocated memory space. So it's going to give up some of its own allocated memory for that communication to happen with another process, in this case process B, right? So shared, this particular area is falling under process A's allocated memory. The reason is process A is initiating communication. So the way process A is going to communicate or send some information to process B here is write that data onto this shared location, and B is going to read information from that same shared location. But the privileges that are associated with this shared region is going to be open for writing only by process A and open for reading by another process, in this case process B. Right? And the kernel is not involved in this case. So this is the reason why shared memory approach to IPC is much faster, because the kernel is not involved. And this is a good option for cases in which you have large amounts of data to be sent from one process to the other. So those are your two approaches. Questions here? Why do we need inter-process communication? What are the two approaches to do this? What is unidirectional? What is bidirectional? Again, even in bidirectional, we could have half duplex or full duplex. And it depends on the type of communication that is happening. All right. Let us take a look at some of the details in these two approaches. The message passing approach is indicated on the left, and the shared memory approach is indicated on the right. You have in the message passing, messages are passed between the processes through the kernel. So a kernel is the intermediary over there. It is much simpler because there is no memory sharing. It is used for smaller amounts of data because this is essentially like passing messages as opposed to large amounts of data. And message passing is very popular as far as distributed systems are concerned, or systems that are connected through a network. For example, a local area network or a wide area network. Why is that the case? Well, because for a shared memory to work, you need some shared memory in a local machine for that exchange of information to happen. But for systems that are distributed on a network, that is not an option. You do not have shared memory in that case. So the only way communication can happen as far as distributed systems are concerned is by message passing. And in that, there are two, in message passing approach, there are two types. There could be a direct message passing approach, or it could be an indirect message passing. We'll talk more about direct versus indirect, but essentially indirect, each process is going to name the other explicitly. And indirect, we are going to use mailboxes or ports to facilitate that communication. So as you can see here, indirect, you are essentially saying, let processes talk to one another by referring to the processes by their names explicitly. And in indirect, you are facilitating communication between processes by using a shared mailbox. And there are some advantages and disadvantages that go along with direct versus indirect, and we'll talk more about that. But those two fall under the category of message passing approach to IPC. Next, shared memory. Over here, what are we doing? We are passing message. We are not passing message. We are exchanging messages through a shared region of memory. It is going to, and that region of memory is going to be in the initiating process, and that is listed over here. Shared memory usually in the memory of the space initiating the communication process. It is going to be much faster because the kernel is not involved in this. It is a good option for large amounts of data, and it is a good option for systems that are not distributed over a network, local machines. Now, in shared memory, you can be using a buffer to move contents from one process to the other. And that buffer could be bounded or it could be unbounded. Now, to explain this, we can use a very popular problem, which is the problem of the producer-consumer problem. The producer-consumer problem is sort of a common paradigm for cooperating processes. Now, for example, if you have a web server that is using files and images which are being consumed or are being read by a client web browser requesting the resource, right? So that's a producer web server, consumer is the client web browser. How are things going to go in that scenario? Producer consumer problem. One solution to that producer consumer problem can be to use shared memory. Now, in this case, we are saying there are two types of buffers. One is your bounded buffer, and the other is unbounded buffer. The unbounded buffer, as the name suggests, faces no practical limit on the size of the buffer. So unbounded. And in that case, the consumer may have to wait for new items. But the producer can always produce new items. It's unbounded. But the consumer has to wait for the new items to come in, because now there could be a long list that has already been put in by the producer. But if you look at it on the other side, the bounded buffer, that is going to use a fixed buffer size. And in this case, two things can happen. The buffer might be empty or the buffer might be full, right, at the two extremes. And the consumer essentially has to wait if the buffer is empty, because now it's waiting for the producer to put in items into that empty bounded buffer so that it can consume those items. So if the buffer is empty, the consumer is waiting. But if the buffer is full, then the producer is waiting, because already it's a fixed size, it is full. So if I want all my items to reach to the consumer, then I must wait, right? So that's sort of what we are talking about in between bounded and unbounded. There are some pros and cons over there. Next, let us take a look at in detail message passing approach to IPC. We are saying that there are two processes, process P and process Q, that want to communicate with each other. And if this can happen, the operating system must offer a communication link. And in this case, we are going to use that message passing approach. So now we are talking about classification such as direct or indirect. How are we going to do this message passing between P and Q? Well, several methods for logically implementing a link and send and receive operations. So we are going to use send and receive system calls to send and receive messages between P and Q. And we'll see examples of how we can use pipes, fork, and send and receive to kind of do this. Now, in message passing, like I said, there could be direct or indirect communication. Direct is you're explicitly naming the process. Indirect is you're using mailboxes or ports to go about that communication. There is another way to classify message passing approach, which is synchronous versus asynchronous communication. So synchronous is also called as a blocking type of communication, and asynchronous is non-blocking. And we'll talk about what blocking and non-blocking is over here. So bottom line, we are still using send and receive system call primitives on a logically implemented link between P and Q, if that communication can happen. And the operating system must allow or facilitate this operation to happen. Next, we are going to take a look at direct communication first, right? So let's take a look at what happens when the processes must name each other explicitly. For me, this is sort of hard coding things, right? Like, because you are explicitly mentioning the processes that you want to communicate with, that boils down to hard coding those process IDs into your process, which may necessarily not be a good thing, because the disadvantage could be that's the limited modularity that you get because of this. So how do you name each other? Well, again, you have send and receive primitives, send and receive system calls to send a message and receive a message. But over here, because it's a direct communication category we are talking about, processes must name each other explicitly. So how are you explicitly naming the process? Well, you're using P and Q, right? the name of the process to which you want to send a message and from which you want to receive a message. You are explicitly putting those process IDs of those processes in as arguments to the system calls, P and Q, right? So these are essentially process IDs of P and Q, right? And that's what is direct communication. Explicitly talk about which process you are referring to. And then the other two, these are what? Message, message. These are message identifiers. Message identifiers. So if you want to send a message to P, you use send, process ID, message identifier. Receive a message from Q, receive, process ID of Q, message identifier. That's where the message that is read or received goes, right? It'll go to the message identifier in this case. So what are the properties of a communication link that is established using direct communication? Links are established by the OS. A link is associated with exactly one pair of communicating processes because you have explicitly named them. Right? So this is going to be for situations where it is exactly one pair of processes that are trying to communicate with each other. And between each pair, there is exactly one link. There are no more than one links in the case of direct communication. And the link may be unidirectional, but is usually bidirectional. So bidirectional allows the user to send messages either way. Unidirectional will not do that. And there are ways to see how you can make a communication unidirectional versus bidirectional. And we'll take a look at some examples, example code to go through those examples, to go through those scenarios. So direct communication, bottom line, put the process IDs of the processes involved explicitly in the system calls. So sort of limiting. It's going to be limiting because changing the identifier or the name of the process, for example, that will necessitate examining or other process definitions, and you would have to change all the old reference identifiers to the new identifier, right? So as you guys might have seen in any programming class, any such hard coding technique where your identifiers must explicitly be stated are going to be less desirable than what? Than techniques that are involving indirection, right? And that is what indirect communication message passing approach allows us to do by using mailboxes, shared mailbox or ports. So that's your next approach, indirect communication. This is where messages are sent to and are being received from mailboxes, also referred to as ports. Now each mailbox has a unique ID. So processes are writing to that mailbox and receiving processes are receiving messages or reading messages from that same mailbox identified by its unique ID. So what are the some of the properties of indirect communication? A link may be associated with many processes because as long as they have the information of the shared mailbox, they can communicate. So many processes can communicate now. Each pair of processes may share several communication lines, not just one, but you can have more than one communication line between each pair of processes. Again, as same as before, links may be unidirectional or they might be bidirectional. So, to quickly summarize, in the indirect communication, we are able to say that a process can communicate with some other process via a number of different mailboxes. Two processes that are communicating with each other only do communication if the processes have a shared mailbox. So shared mailbox is sort of our go-to in indirect communication. So direct communication is not used in today IPC. Well, so for simple messages in which so your application has to drive that choice, right? So if your application is such that you want to be absolutely be explicit in terms of which process it starts from and which process the message is going to, then direct communication is an option there. Again, it falls under the category of message passing, so it's suitable for small amounts of data, but your application will drive that, right? So a shell mailbox has a lot of advantages. Clearly, you are able to do that in direction. Don't have to hard code things. But if that is sort of a requirement to a user, then they may choose direct communication. But in general, you can see indirect communication is much better because it has all these advantages, and many processes can do this, and many communication links can exist. So it's not very limiting. All right. Let us take a look at what are the operations that are involved as far as indirect communication is concerned. What are the operations? Well, we need a mailbox, right? So if you need a mailbox, then you need to create a mailbox. Create a mailbox, send and receive messages between processes through that mailbox, and at the end, you destroy a mailbox. The primitives that are being used again are send and receive, the same primitives. However, there is a difference in terms of how the processes are being identified. Here, we do not have P and Q. What we have is mailbox unique ID A. Mailbox unique ID A. Still, we have message identifiers for the message that you want to send and receive. However, you have a unique ID that is going over there. Mailbox unique ID. So all you have to do in order for you to change that communication is change the unique ID, right? So you can sort of do that in direction. You're not hard coding things by doing this indirect communication approach. These two are still message identifiers. Next, we talked about the other two types that fall under this category, which is synchronous communication and asynchronous communication. So let's talk about what is synchronous or blocking, and let us talk about what is asynchronous or also called as non-blocking communication. So whether it is direct or indirect, message passing may either be blocking or non-blocking. So it applies to both mailboxes, and it applies the same way to messages being passed between in a direct communication approach. So what is blocking? Blocking is also considered synchronous. In this case, blocking a process is blocking that can again use send and receive system calls. So what's a blocking send and what's a blocking receive, right? So for a blocking process, the send and receive system calls are going to be blocking send and blocking receive. So what's a blocking send? It is the case where the sender blocks, essentially waits until the message is received by the receiver. And blocking receive is the receiver will block or wait until a message is available. So available by the sender. So a sender is going to be waiting until the message is received by the receiver, and the receiver is going to be waiting until the message is available by the sender. So if the sending primitive is of the blocking type, your sending process is blocked until the message is received by the receiving process or by the mailbox, because it's the same way for indirect communication. Now, how does it change as far as the non-blocking send is concerned? Non-blocking, also called as asynchronous. Non-blocking send primitive is going to be non-blocking send is when a sender sends and continues, right? So it's not trying to synchronize with the receiver receiving it. It's not waiting. The sender sends the message and then continues. While a non-blocking receive is when the receiver receives a valid message, or it's not receiving anything, none, right? So non-blocking, there is no wait. It's a more continuous process, and it's asynchronous. In the case of blocking, it is synchronous because you are sort of changing the way you communicate by forcing the sender and receiver to wait for one another. Wait until message is received. Wait until message is available. Right? So that's essentially your difference between blocking and non-blocking. Next, in the case of buffers that are being used, message passing approach through buffering, messages may reside in temporary queues, right? So we are talking about buffers or temporary queues. Those are being used to do this message passing. So one was direct, one was indirect, and then now we are talking about how we can use buffering to pass messages between processes. This again could be direct or could be indirect. So it could apply for messages or could be with respect to a mailbox. So a buffer or temporary queue could be implemented in one of the three ways. One is zero capacity buffer, the other is bounded capacity buffer, and the other is unbounded capacity buffer. So if it is zero capacity buffer, then the queue has a maximum length of 0, which essentially means that the link cannot have any messages waiting in it. So in this case, obviously the sender must block until the receiver receives the message. And because of this, only one message can be sent at any given time. Again, we are using both the send and receive system calls, and both are blocking. 0 messages in the maximum length is 0. Now, let's talk about bounded capacity. Bounded capacity buffer is when there is a finite length of n messages. Now, the sender must wait if the link is full, just as we talked about the producer-consumer problem. If we are talking about a buffer, bounded buffer, then the producer must wait if the buffer is full. The same way, finite length messages, n messages, the sender must wait if the link is full, which essentially means that the sender must block until space is available in the queue. So the receiver has to get those messages, empty out the queue. Maybe it does that in a first in first out basis, or it does it in a different scheme. But whatever it is, it has to get those messages, empty some space, and then the sender can unblock, right? So if the buffer is full, which happens in the case of bounded capacity buffer, the sender should block until there is a space available in that queue. Now, in the case of unbounded, now we are talking about infinite length of the queue, and the sender is never going to block. But the problem with the unbounded capacity is, if the consumer has to look at a new message, then it has to wait for all the old messages to be consumed to get to the newest sent message. Because usually whenever you are trying to fill up this queue or buffer, typically it happens in a first in first out basis. So whatever you put in first gets out first. So if the consumer is interested in looking at the most recently sent item, it actually has to go through this infinite length queue, which could be really long, to look at the most recently made available item, right? So this even though in theory sounds very very advantageous, in practice it is not really advantageous, because you want, more important than the capacity of the buffer, there is another aspect to it, which is sender is sending messages because it wants them to be received by the receiver. But if the receiver is going to receive that message very far out in time, then it might really not help the application. So I hope you guys see the difference between that unbounded capacity buffer and the unbounded capacity buffer, the differences between those two approaches. In general, a bounded capacity buffer with an with the application driving the size of that buffer works really well. You don't want it to be too small and you don't want it to be too long. All right. Next, let us take a look at pipes. Pipes are system calls that are going to allow a channel to be established between two processes. And then we can use these pipes to sort of pass messages between one process and the other. So let's take a look at some issues that might need to be answered while we talk about pipes. The first thing is the communication unidirectional or bidirectional? Well, again, this one is going to depend on the type of pipe. So we can have classification even in pipes. You can have ordinary pipes, you can have named pipes, and there is other types to classify them as well. So it depends on the type of pipe that you create. Pipe is essentially a channel, right? So channel on which you are trying to communicate between two processes. That link, that channel can be unidirectional or bidirectional. Okay? It depends on the type of pipe. And if it is bidirectional or two-way communication is possible, then the next question is it half duplex or is it full duplex? Half duplex means that both processes that are involved are able to send messages and receive messages from the other. But half duplex is only one can send to the other at any given time. Full duplex is both can send messages to the other and receive them at the same time. Next, another question is, should you have a parent-child relationship between the communicating process, or such a constraint does not exist? For example, if you're talking about ordinary pipes, that has to have a parent-child relationship between the communicating processes. But for named pipes, such a relationship does not need to be there. Next, can the pipes be used over a network, or are they restricted to the local computer? Again, it depends on whether you're using message passing or you're using shared memory, which type of approach you are using. Also depends on ordinary pipes and named pipes. How are you classifying that type of pipe? So let's talk about this difference between named and ordinary pipes. Ordinary pipes are more or less temporary pipes. They are inaccessible from outside the process that created it. So for example, if there is a parent and a child, a parent is there, there was a fork system call, and it created a parent and child relationship. So typically a parent process creates a pipe and uses it to communicate with the child process that it created. So between a parent and child, in a parent-child relationship, you may be interested in temporary pipes that facilitate communication between parent and child. Those are classified as ordinary pipes. Named pipes can be accessed without a parent-child relationship. So this, because we are naming the pipe. And when you name the pipe, you can allow communication outside of this parent-child relationship. Let's take a look at ordinary pipes. These are temporary, meant for communicate. Oh, by the way, when you look at pipes, this falls under the category of message passing. So we are not looking at shared memory. We are looking at pipes are message passing approach to IPC. So let's take a look at ordinary pipes. Ordinary pipes are temporary. The application of ordinary pipes is for temporary usage. You don't want that pipe to exist for a long time, just temporary. Ordinary pipes are allowing communication in a standard producer-consumer style, which essentially means unidirectional. Producer is sending it, consumer is receiving it. temporary communication, unidirectional communication between two processes that are in a parent-child relationship. That's where ordinary pipes are being used. So producer, or the sending process, writes to one end. Where are we writing? We are writing to the right end of a pipe. And a consumer is going to read from the other end of the pipe. Pipe is a channel. We are writing to one end of the pipe and you are reading from the other end of the pipe. So the producer, unidirectional communication. So producer is writing to that end, right end, and a consumer is reading from the other end, called as a read end of the pipe. And as we said, ordinary pipes require a parent-child relationship between communicating processes. So let's take a look at this diagram over here. What do we have in this case? In this case, we have a parent over here and a child over here. And there is a pipe or a channel that is sketched in the middle, which is being used to pass messages from parent to child or child to parent. Now we are using file descriptors. FD stands over here for file descriptor. FD, file descriptor. And you're using two of them, FD0 and FD1. So FD0, FD is an array of two elements. The first element, or 0, is FD0 is being used to read from a pipe. And the other one, FD1, that's a file descriptor that is being used to write to a pipe. So that's an important thing to consider. Our file descriptors that we are using, 0 is being used to read, 1 is being used to write. Now if I go here and take a look at this, you see FD0 for a parent is pointing to this end of the pipe. FD0 for the child is pointing to the same end of the pipe. So this you can conclude that is the read end. That is the read end of the pipe. And again, FD1 used for the child to write to the pipe. FD1 parent used for writing to the pipe. Right? It's the same file descriptor, but when it is used in the parent is writing to the pipe. When it is used in the child is using to write to the pipe. So both of these combined, you can say that is the right end. It didn't work. That is the right end of the pipe. Right? So both of these guys, parent and child, two processes, sending messages from one to the other. Now, how does a parent send a message to the child? Well, you have to write the message. What is the parent going to use? Parent is going to use FD1 to write the message to the pipe, and then child is going to use FD0 to read message from the other end. Right? So that's how the communication is going to occur between parent and child. So let's take an example over here where we create a temporary ordinary pipe between different processes. Here we have three processes that we are using as an example. You have ls, which is used in Unix environment to list out all the files in a current working directory, ls. Then we have a grep apple, essentially searching for the string apple in the name of the files. That's your second process. Then you have more, which is essentially show me the details of or display the contents of files. So list out all the files, search for the string apple in the file name, details of the file. So those are three different processes that are appearing in this particular example. But what are we doing? We are using two pipes. There is pipe 1 over here And there's another pipe over here. So we are taking the standard output of ls, which is essentially contents of the current working directory being written on the standard output, such as a monitor or a screen, right? So pipe the output, the standard output of ls to the standard input of grep apple. Now we can, so what are we doing in this grep apple? We are essentially searching for the string apple in the file name of all the files that we have listed in the previous process, ls. So now both of these combined, this will show you all the files in the current directory which have apple in its file name. And then we are taking the standard output of both of these and piping it to the standard input of more. So that will allow you to display contents of all those files in which there is apple in their file name under the current working directory. So that's essentially how a quick example of how you can create. These are ordinary pipes. As you can see, we have not named the pipes. Between three different processes, you have created temporary communication. Standard output of one pipe going into the standard input of the other. Next, let us take a look at named pipes. They are more powerful than ordinary pipes. Communication can be bidirectional. You can have more processes participating in this communication because no parent-child relationship is necessary now. Now, several processes can use the named pipe for communication. So as long as you know how to identify that pipe, you can use that in any process to communicate. They are provided both in Unix as well as Windows operating systems. So there's a very comprehensive example that we are going to work through, in which we will see how we can use named pipes. That brings us to the message passing example using the Unix system call pipe. So this system call will create a link that appears to a program like a file, but it's not a file, that one process could read to or write to, read from or write to. So let's go through this example. We'll spend some time talking about how does that communication happen. The first thing that we are doing is initializing pipe fd as an array of two file descriptors, right? That both integer data type. Pipe fd is my two file descriptors. I'm just initializing it. Then I have the Unix system call called pipe, and I'm passing pipe fd as my argument to the system call. Now this is going to return two things: pipe fd0 and pipe fd1. And the process in which this is available can use fd0, the zeroth element in that array, for reading, and pipe fd1, element number 1, for writing. And we can take a look at this over here. We have this first in first out pipe buffer. There is a process P, and maybe there was a pipe system call that occurred in process P, and the moment that pipe system call happened, it returned two file descriptors: pipe fd0, pipe fd1. This was used to read from the pipe buffer, and this was used to write to the pipe buffer. So this is and of course this is just the this is as you can see, this is not real communication, right? Because there is nothing else. I need another process. So this is incomplete right now. So this, I'm just laying out the basics here, because we are going to build on it. One process, buffer, there is no communication here. There's no second process involved. So the point is, I'm using this guy to fd0 to read from first in first out pipe buffer, and I'm using this guy to write to the same thing, write to p4 pipe buffer. As far as process P is concerned, right? So process P is going to use these two file descriptors to pass information to that pipe buffer. But again, there's no communication because there's just one process. We need to have another process in the conversation. Next, a read from pipe 0 accesses the data written to pipe FD1. So whatever you write to pipe FD1 can be read from pipe FD0. Those are your file descriptor identifiers. And we are doing this on first come first out, first in first out basis. And we'll talk about, so when we put a child into this conversation or a consumer in this conversation, we'll see what could go wrong if the communication is not first in first out. Also note that a computer system has a standard input and a standard output. And a standard input, such as a keyboard, any process that is trying to read information that is being sent by a keyboard uses the file descriptor of 0. So the file descriptor itself is 0. It's not the 0th element of the file descriptor. The file descriptor itself is 0 for standard input. So a process can read information from keyboard using 0 as the file descriptor. And for standard output, which is say a monitor or a screen, the file descriptor is a 1. So if you want to show something on a monitor, use the file descriptor 1 and that will pop a message on the screen. So that's for standard input and standard output. Different from the input and output of a pipe. All right, so all we did over here is we have just created those two file descriptors, pipe fd0 and pipe fd1. That's all we did so far. And the buffer that we are using is based on a first in first out. Whatever message you write first will be read first basis. Next, we'll continue this example. What we are using is we are setting up one-way communication between two processes, between a parent and a child. So one-way pipe from a parent to a child is what we are setting up. So we have a main function call over here in which first what we are doing is we are declaring fork value, and child PID as integer data type. And then we have pipe FD, which is an array of two file descriptors as again integer data type. Pipe value is also of integer data type. And then we have a 100 character buffer, and n bytes is of character data type. So we have essentially set up things in terms of all the variables and arrays that we are going to be using. Buffer is 100 characters, pipe FD is two file descriptors, everything else is integer and or character data type. Next, before we actually fork, because we are going to actually need to fork to establish a parent and a child, before we fork, we actually set up the pipe, because we don't want to set up two pipes in parent and child. We want to set up the pipe first, and then we can do the parent and child creation. So what we are going to do is pipe is the Unix system call to create that two file descriptors for reading and writing to the pipe. And we are passing pipe FD, which we have initialized over here, array of two elements. So that will return pipe FD0 and pipe FD1, right? So that will return two file descriptors, pipe FD0 and pipe FD1, one for reading, the other for writing to the same buffer, pipe buffer. Now, if that return value, instead of being two file descriptors, if that return value is less than 0, that essentially indicates that you were not able to open the pipe and you exit out of that unsuccessfully, right? Terminate out of that unsuccessfully. So here we have parent, FIFO buffer, two file descriptors, one for reading from the buffer, one for writing to the buffer. We have not put in a child into this conversation yet because we have not used the system call called fork. We have just set up the pipe. We have just made the two file descriptors. Next, the second step that we are going to do is to use the system call called fork. And the return of the fork system call is being stored in integer data type fork value. And as you know, the fork from the previous lecture, fork value is going to be 0 in a child, and it is going to be the process ID of the child inside a parent. That's what fork value has. Now, the first check we will do is if the execution of the fork happened successfully or not. And if the fork value is equal to -1, that essentially indicates that there was an error of executing the fork. And that's what we are indicating over here. We are printing out a couldn't execute fork statement, and we are exiting it out of the if statement unsuccessfully. But if the fork happened successfully, then we can check whether the fork value is going to be 0 or no, not 0. Because if it is 0, then that indicates that it is a child process. And if it is not equal to 0, then it indicates a parent process. Right? So let's take a look. The moment fork happens, you have two processes, parent and child. Both of them are exactly the same, and they are trying to execute this next instruction. Looking at the fork value, they are both getting executed concurrently at the same time. So let's try to see what happens in the child, and then let's also take a look later on at what happens in the parent. So in the child, what is going to happen? Well, you go through this, and if it was successful, you check for fork value equals 0. And in the child process, it is actually going to be 0. So what do? You do a printf. What are you printing? Child says my process ID is whatever the return value of get PID is. Get PID is a system call that is used to return the process ID of the process in which that system call occurred. Right? So it is essentially going to return the process ID of the child process, and it is going to display that as in the form of a printf statement. So that's what is happening in the child process. Now let us also take a look at what is happening here in this diagram. You have the parent and you have the child. You have the P4 pipe buffer right in the middle. You're using pipe file descriptor 0 and 1. The parent is using pipe file descriptor to read from the buffer, and the child is using pipe file descriptor 0 to read from the buffer as well. It is meant for reading. Read. And this is for write to the pipe buffer, and this is for the write to the pipe buffer. Now what we are going to do is we are going to pass a message from the parent to the child. And in this case, if you want to pass a message from parent to child, you don't need to really write to the buffer from the child. So what we are going to do in the child is close this guy out. And similarly, we are later on, when we are in the parent, we are going to close this guy out. So what we are going to do is write to the buffer using parent and read from the buffer using the child. That's all. One-way communication. So we are going to take turns and close out those ends as far as the child and the parent is concerned. So right now we are in the child, right? So because we conveyed the fork value, it is 0. So we are trying to go through the child right now. You printed this particular statement first. Child says my PID is whatever that integer comes out to be. Then the child closes the right end of the pipe. How does it close? In the child, there is a system call again. Close followed by pipe file descriptor element number 1. So that is out. It closes the right end of the pipe as far as the child process is concerned. Next. From now on, the right end is gone. It can only read from the pipe. How is it reading from the pipe? Well, we are using the read system call to read from the pipe. Well, what is the file descriptor used to read from the file? It is pipe fd0. Pipe fd0, as it is over here, is being used to read from the FIFO buffer. What are you reading? You are reading buffer. What is the size of the buffer? Well, you can return that value by using size of buffer. So you're trying to read the read end of the pipe in the child, and you're reading from buffer the size of the buffer, those many characters you are reading. And if this returns n bytes, and if n bytes equals 0, that essentially means that there is another error in which the child returns could not read the pipe. So read function call has three things. One, which file descriptor are you using to read? Where are you reading from? How much are you reading? How many characters are you reading? All of that is returning the number of bytes. And if the number of bytes that you have read is less than or equal to 0, then you say couldn't read the pipe. Again, we are continuing in the child. Next, what we do is we are looking at write. Write out the data to the standard output. Again, this is not the child writing to pipe fd1. This is the child writing to the standard output, in which case the file descriptor itself is equal to 1. So that's what we are using here. Write 1, which is the file descriptor for standard output, such as a screen. And on the screen, what are we writing? We are writing child : this is what I read from the pipe, followed by 41 characters. And then you are saying, I will also write to the standard output, to the screen, whatever value gets stored in buffer of n bytes. So all those n bytes in buffer, I'm going to write over here. Right? Soon after, child, this is what I read from buffer. After these 41 characters, I'm going to write whatever is there in buffer. Whatever I read, what is in the buffer? Whatever I read from the pipe file descriptor 0. So when you read pipe file descriptor 0 from the buffer, it is of whatever size, in this case n bytes, that is what you're writing to the standard output. So this is essentially like read from the read end of the pipe and display whatever you read onto a screen. That's what the child is doing right now. And then you successfully exit out from the child. So you see, all the child is doing is closing out the right end and reading from the read end and displaying certain characters onto a screen, on a monitor, standard output. That's all. And when it is executing read, that's when it is getting the information from that file descriptor to go into that buffer. That's what it is displaying over there. All right. So while the child is doing all of this, what is the parent doing? Let's take a look. Else. What is this else for? The fork value, right? If fork value was equal to 0, it did all the child business. Now else, it is taking a look at the parent. It is the first thing that it is printing is parent. My PID is whatever the system call get PID returns. So if you have get PID, whatever it returns, it is going to return the parent, the process ID of the parent, and we are going to display it first. Then we are going to say the fork value inside the parent. You see, inside the parent, let's point out here. In the parent, fork return value of fork is in the parent return value of fork is PID of child, right? We have seen that before in the previous lecture. So that's what will be currently in the fork value. So we are making that value go into child PID, and then so literally what the parent print is printing first is parent. My parent is process ID of the parent. Then it is saying parent, my child's process ID is whatever the fork system call returned in the parent process. So it's saying my process ID is this, my child's process ID is this. That's the first thing it is doing. Next, we are going to close out the read end of the pipe as far as the parent is concerned. Like I said earlier, I only need, we had already closed this out, I only need to do this and this. Write to the buffer and read from the buffer. So I'm also closing out the pipe FD0 as far as the parent is concerned. Next, all I need to do is I've already set up reading from the child. We have already done that. The only thing left is for the parent to pass a message to a child using pipe file descriptor 1. So that's what we are doing here. So from now on, the parent can write to the pipe. And the first thing before it actually writes to the pipe, what is it doing? It is writing to the standard output onto a screen. What is it writing? It is writing parent, this is what I wrote to the pipe. Just some string of 41 characters. Remember, these are ASCII characters, right? So ASCII characters are character. Each character is what? 8 bits, right? So 1 byte. So there are 41 bytes that are going in this, and you can calculate, you can count the characters, and you will see that there are 41 characters over there. So what are you writing first? You are writing parent, this is what I wrote to the pipe. Just a string of 41 characters. Next, what are you writing to the screen? Again, standard output 1. Hello BB, new line character, 12 bytes you are writing. So far, the parent has written a few things. One, parent, my process ID is so and so, my child's process ID is so and so. Then parent says, this is what I wrote to the pipe, and it is saying that it wrote hello baby to the pipe, but it has actually not written to the pipe yet, right? This is just going to the screen. This is where it is writing to the pipe. Let's take a look. Write. Where are you writing? Pipe file descriptor 1. What are you writing? Hello baby, exclamation point, new line character. 12 bytes are being written to file descriptor 1. And if all of that does not equal 12 characters, then the parent could not write to the pipe, essentially exiting it out. But if that equals 12, that indicates that all those 12 characters were able to go on to the file descriptor 1. They were written to the first in first out buffer. So parent is writing to the buffer once, and then the child, whenever this is ready, is going to read from the buffer. So the child essentially is going to get what? It is getting hello baby, exclamation point, new line character right here. Where is it getting? Right here. In its buffer, that's what it's getting when you do the read. So this is how you can, pass a very simple message from a parent to a child, and then you're exiting it out successfully. All right, so that's all I have for you guys. I hope that was helpful. Oh, by the way, let me talk about first in first out. So if you have a first in first out buffer over here, producer or parent puts a value in there, and the consumer or child is trying to read it, right? On a first in first out, whatever goes in first comes out first. Let me ask you, what would happen if this was last in first out? What would happen then? So message 1 message 2, message 3. Suppose there are 3 messages being sent by the P process. If they go on to the buffer and then later on being read by a child, they will be read in that exact order, right? M1, M2, M3. But what would happen if it was a last in first out buffer? Ideas? It could be M2, right? So different order, right? It would be scrambled order, but in the worst case scenario, it would be M3, M2, M1. The reason is the child might be reading at any given time, right? So maybe it reads when M2 was written, maybe it reads when M3 was written. So if it reads after M3 is written, then it will read in the exact reverse order, M2, M3, M2, M1. The messages are being received in the exact reverse order. Or if the child reads after M2 was written, then it is doing M2, then maybe M3, then M1 in a scrambled order, right? So that's why you don't do last in first out. That's why you actually do first in first out, so that the messages are received exactly in the same order as they are sent. All right, that is all I have for you guys. I'm gonna erase all of this and stop recording, and then you guys can work on the activity.